Alright, time for another DraftPhysics.com video presentation. DebatePhysics.com also, and such. And this debate is... it shouldn't be all that difficult to get people to stay somewhere on the subject, but apparently it is impossible. Pretty much. So the subject is we're looking for some experiment that provides an opportunity to understand that one theory versus another theory. So there's a competition between mv and 1/2 mv squared. And the simple argument is they are not compatible. There are two different theories of the reality, and they both can't be right. One of them's the correct answer, one of them's the wrong. For the definition of what energy is in the universe, or a quantity of motion, whatever you want to call it, the stuff that makes things move. Now, I've observed that a lever is a pretty basic telling object. It'll explain to you, it'll tell you the truth. Okay. Spaceships and other things will also tell you the truth, that momentum wins and kinetic energy is, as I stated, just a fable. It's just a gremlin theory, and it has nothing to defend it. It's every experiment that indicates anything close to it is just misunderstood. It's because people are in fact really ignorant, but they're pompous and arrogant and all that crap. I mean, it can be simply understood why it requires 4 times the distance, okay, for something to acquire twice the velocity, because it's about the time. You're in the force, that's a 9.8 meters per second per 1 second force, and you're only in the time, you're only in the force twice as long here. 1 unit of time here, 2 units of time here. That is twice the velocity, twice the weight, and twice the time. Okay, not this 4 times the distance is just a fact that once you acquire a velocity, you don't lose it until something opposes you. So you gain the velocity here of 9.8. Okay, you go 5.4 here in the next second. And you just add the 9.8 to the 5.4, and yeah, that's all you get. And then the third second, you only get 5.9. You only get 4.9. Geez, get it right. So, I mean, I've explained all of this. It makes perfect sense. It also explains why rolling things roll 4 times the distance or more, actually, versus, 1 to 2 velocities versus 1 velocity. And there's this stark difference, 4 times the distance. That's because friction isn't linear. It isn't the same amount of friction per inch. Okay, it's the same amount of friction per time. This only takes 2 units of time. This takes 1 unit of time. What you're doing here ends up being the same as what you're doing here. You're going half the speed way over here. Jesus. I mean, why is this zoomed in so much? I'll have to figure that out. Anyway, so again, the demonstration. 4 times the distance, only twice the velocity. Because you're losing to the ground less here, okay, the whole 3/4, this whole section of banging into the ground, actually be the same much disruption of the ground as this little section. So the 1/4 equals the 3/4, and the fact is the time works out exactly that way too. This is 1 unit of time, this is 1 unit of time. It perfectly makes sense. Okay, they're not going to refute any of this. They're not going to show how I just lied about how it works at all. They won't draw it. They won't explain it. They won't show it, because they'd have to concede the argument if they did. Okay, they won't do that. They cannot possibly do that. All right. So I've explained how levers balance. Okay, and they balance. I can put the 1 mass, 2 units of distance, 2 mass here, and those two balance. Okay, whether I put them above there or below, or I hang the fulcrum here, or I hang it works, and it will oscillate. Okay. Yes, except for the one extreme, I guess, where I put all the mass in line with the fulcrum or something, then it won't balance. then it goes anywhere, I suppose. But that's what they argue anyway. Who cares though, really? We know that when it's in these conditions, it does work as a balance. And the fact is, this will, if I put any energy in, that's right, disrupt it in some way, I provide a force. And in gravity, what basically gravity is a battery. You're just putting the energy back and forth, and it will oscillate perfectly. Okay, so the whole thing will just oscillate with that force in it until the force winds down, just like it was a pendulum, and indicating that these two have the same energy. That the two mass going the short distance and the one mass going the twice the distance means the same thing. They equal the same amount of energy, and there's no reason to believe that this is correct, because this formula says this has twice the energy. Twice the number of joules of energy are happening over here, and only 100 here, 200 here. All right, so the other simple experiment would be to place something. Let's have a lever that's horizontal this way, and let's just knock things into it. This one is way out of line. It should be here. All right. So what happens when I put a 2 mass and a 1 velocity, okay, into this side of the lever? Can I expect the 1 mass to leave with 2 velocity? And my argument is yes, you can. And that would be creating free energy. So that would prove this theory wrong. So if I can put a 2 mass at 1 velocity, hit the lever here, push this object at twice the velocity here, 2 velocity, just 1 m, I will have in fact, generated by their theory, free energy, because this would have the 200 joules and this would only have 100 joules in, so that's free energy. And we know that doesn't work, because we'd all be using it if it did work. So it clearly doesn't happen. It proves that this is, as I state, garbage. And levers do in fact conserve momentum, and they will, in this configuration, do something impossible. They'll make free energy. Well, what if I do it the other way around? What if I drop the greater joules of energy, the 1 mass going 2 units further on the lever, and I have the 2 mass here, what's my expectation? Now, they won't answer the question, because by their energy rules, this is only half the work. So yeah, this should shoot off at twice the speed, but it's only half the work. I mean, we've got 200 joules here. Making this go 1 unit of distance isn't going to do it. I mean, it's not going to equal the 200, so somehow they're going to just argue I lost 100 joules. I mean, 100 joules just flew out of the universe, disappeared, because they won't show how this lever this fulcrum got any heavier or any more force was on it. And the truth is what they're really saying is that I could put two masses here. I could put 4 mass here, and expect it and be the same joules. This 4 leaving with 1 is going to be the same as this. So that's their theory, that I could theoretically, if levers do conserve energy, I could put the 200 joules in this form, and I could take the 4 mass and move it at 1 velocity. That would be equal in their mathematics. That would have conserved the kinetic energy. So that's what they actually believe. They believe the energy in a 1 mass moving twice the velocity is actually the same as a 4 mass, moving 1 velocity. That this should be able to make this. That I should be able to make 2. I should be able to move 2 10-ton trains. You can see that? Yeah, almost. I should be able to make 2 10-ton trains going 5 miles an hour. Out of just 1, 5-ton train going 10 miles an hour. That they say these two things are equal. 2 10-ton trains going 5 miles an hour is the same as 1 10-ton train going 10 miles an hour. I mean, it's just saying this is nonsense. Okay, I've pointed out it has no good history. It has no evidence on its side. They'll never show you a video where it takes 4 times the fuel to go twice as fast. And yet they keep arguing in defense of this crap. And they're not really arguing it, right? They're evading the argument because they won't draw the lever, they won't draw the spaceship, they won't draw gears, they won't draw anything and show how their theory has any continuity or makes any sense at all. So, having done that, so yesterday, there's this silly argument about what exactly how the lever functions, and the argument is somehow it doesn't function if I attach the weights at the top, because then as it's tipping, this side gets further, which means it should stop tipping and reverse, and it doesn't, and all this mush that I can't really figure out exactly how this has anything to do with anything. So I show a video where it's clearly illustrated that the fulcrum is way below the center of the lever, and the weights are put way above the center of the lever, on top of. And this would be the typical configuration for anybody who does the experiment by putting a log on the ground and putting a board on it and then have 2 people stand on it. And of course they can balance, they can put just enough weight to make it totter a little bit. It's called a teeter-totter. They can make that happen. And yes, I would argue it's less stable, but it does work. And so, whatever theory you have about how balances work, it has to include all of these examples. So clearly this is an example where it works. So we'll just play the little video where he's putting the weight on.
Twice as long
so
as the other.
Clearly the weight is hanging from the top of the lever. No doubt about it. Really shouldn't be an argument here.
Let's put a 10-pound weight on this end, and now we'll...
it's clearly putting the weight on top of the lever. Okay, so there's really no argument
put half
here.
as much weight on this end.
Okay.
5 pounds, balance 10.
And that's what happened.
If we have...
All right, so, is there something to argue here? No. Okay, that happened. And this lunatic, asshole. It's not really, I don't want to insult lunatics, because, this is too stupid. Okay, so he still wants to argue some theory that this has to do with the attachment point on the lever and how close it's getting to the fulcrum, and that decides whether it's stable or unstable. So I played a video basically talking about center of gravities and how if whatever you're balancing is below your center of gravity, then you're more likely to be stable, and the higher it is, the less stable it is. And I think that's reasonable enough as an explanation. I don't know if we need even more details than that. But he just insists on making this video insulting me as if I'm, as the title says, a liar or an idiot, because I showed a video where what he says can't happen, happened. Yeah, so that's my bad. It's just too ridiculous. This is so off the subject. It really doesn't have anything to do with proving that levers conserve kinetic energy, rather than levers conserving momentum.
For the final time.
Okay, so for a final time. So somehow this is a decisive proof. He's proven Chevrolet to be liars. Right? All I did was play a Chevrolet video showing a lever with the weights on top of the lever. Pushing down on the top of the lever. Why does that make me a liar?
Geometry works.
So again, the simple argument is this geometry. Yes, it makes sense. Okay, yeah, I drew it. That's I think that's how this subject even got started. Is that I pointed this out. That this one gets closer as it drops. One line gets closer. This corner gets closer to the fulcrum. The other gets further in terms of its straight distance in horizontal space. But the catch is when you put the weights at the top, it doesn't. It does exactly the opposite. And the two of them kind of have to behave the same because they both have an element of instability.
Stable condition, equidistant arms and forces. Displaced, unstable. Displaced.
I don't know why he says unstable. It balanced. So that wasn't unstable.
Unstable. It doesn't oscillate backwards and forwards.
That's oscillating back and forward is not unstable. Unstable is when it oscillates all the way around. All right, you still haven't got that part right.
Because the things are swinging about. But it would oscillate. But the point is unstable. Unstable.
I don't really understand why he's using the word unstable when it's balancing. That's the definition of stable.
In that position, it's stable. Turn it over.
Too silly. So instead of flipping it over, he turned it over, which means if he's got this fulcrum at all, if there's any more mass on one side of this lever than the other side, then he just sit there and reverse the problem while he's reversing the thing. So, I mean, obviously you could get the effect. So he should have pulled it off and reversed it.
Top corners. Geometry.
All right, so he wants to argue that somehow this proves that the other video didn't happen. Okay, that whenever you hang the weight from the top of the fulcrum, the top edges, the thing can't work for some reason. I mean, obviously it does work. So why are you making this argument? Obviously this has something to do with how small your lever is and, its dimensions, how thick it is versus how long it is. Apparently all these things do matter. So it's more complicated than your simple explanation. Your simple explanation isn't consistently working, so why are you defending it? I mean, I said in the video, I don't know exactly how it works. I theoretically can't really explain why a lever balances, because frankly, once the one weight is lower, it's heavier now. It's in more gravity. Technically, it's closer to the earth. It's in more gravity. Why would it stop moving? And my only explanation is the only cause I can blame is something to do with the friction. The amount of friction takes away a little bit of the energy. And as it takes away the energy at E, it basically is saying I haven't sufficient energy to lift the other object because I lost some of the energy from friction. So I can't lift the other object as high because friction took a little bit of the energy I'm using to do it. And therefore I can't do it. It has to stop. And once it stops, then it can reverse. But why it reverses, I'm not sure.
It works again. It was predicted that it's unstable when it is.
So again, what's the point of this? I showed the lever working in this configuration. So that's all my obligation is, I think. I showed a pretty credible source where the lever does balance. So whether you're tilting them too high, whether you're doing something, there's obviously some difference between this lever and that lever. And that's what you should be explaining, is why that lever balanced and this lever isn't. But you're not doing that, obviously. Maybe it has to do with the obvious difference is their lever didn't have a bearing in the middle. That was the fulcrum. The fulcrum was at the bottom of the lever. Fulcrum was lower.
Geometry works, of course. I think Newton and Descartes and Galileo would all agree.
Okay, so he thinks, and based on what? So again, I've made the point that Newton, Galileo, and Descartes all understood quantity of motion. They understood the universe was made out of momentum, and they got a lot of right answers. I've made that statement. He's pretending that Newton and Descartes and Galileo believed whatever his theory is here about this distance thing, and that's why levers work. But he hasn't explained any of that, shown any reference to that. So I call bullshit. Really, there's no point in playing these videos. This is just so obnoxious. A liar or an idiot, because I just point out that now your theory doesn't really work. It doesn't consistently show itself. Again, I can show people standing on levers that are configured this way, and they can make them balance. So why are you arguing they can't?
Unstable again. Once it turns over in any position, it's unstable.
So he just, it's just he switched them again. So now they're back to the other configuration. So the only part of the video he has them in this unstable condition, or whatever he wants to call it, is this
Top
little
corners.
portion.
Geometry works again.
So he's holding it, okay, but he didn't let it just balance. And again, he is tipping it to like this 45-degree angle. Who knows what the exact I don't know. I'm just saying this arrogance is just so pointless here. What's your point? So this has nothing to do with kinetic energy. I mean, nothing. I don't know why it's relevant. And yeah, it's okay, it's kind of an interesting subject, but I'm just pointing out how your theory of how it works can't be true, because obviously some configurations where the weights are hanging from the top do work. So why are you arguing this shit?
It's predicted that it's unstable. When it is, it wants to turn right over.
So he's calling it unstable when it turns all the way over is somehow stable. Doesn't make much sense. Now, theoretically, the argument could be made. The weight down here is in more gravity, technically more gravity. So why wouldn't it just keep spinning? That would be the question. The question is why does it go back in other configurations? Why does it attempt to balance?
Geometry works, of course.
So he says geometry works, of course, and you're just like, what the fuck are you talking about? The argument is, I'm showing you two videos. One of them you're showing it doesn't work. The other one shows it working. You have to explain the difference between those two levers. What is different about your lever and the Chevrolet lever? What's the difference between those two levers? Why is yours not behaving very well and theirs behave fine?
I think Newton and Descartes and Galileo would all agree. Unstable again. Once it turns over in any position, it's unstable.
I guess it's just so funny. It's unstable. Anyway.
Either
Continue.
side, predicted by the geometry.
So the argument is that Julius Sumner made, and I'll play another Julius Sumner video in this video, because there has to be some kind of better content than this shit. His argument was like basically the weights above, it's unstable. Weights below the fulcrum, stable. And he's reversing that language for whatever reason.
Only stable in that position because of the equidistant arms.
So they're all equidistant arms. I don't know, what the point is here. And again, it works as a balance, and that can be shown in both of these. Whether I hang the weights from the bottom or I hang the weights from the top, I can get it to balance. So again, I don't know what point this is. He's clearly, again, yes, you can make a rectangle, a different size lever and change its capacity to balance. That might be the point. That levers of, where you're changing the total length versus the total width, that just start fucking with the function of the lever. Okay, I'll agree that maybe that's possible. I don't even know if he's arguing that.
Go back to bloody school, you prat.
Go back to school, you prat. So there's no, again, he's just overtly saying, look, I'm right, the Chevrolet video is somehow a lie. So he's calling, Chevrolet a liar and an idiot, because they did a lever demonstration and it worked, and the configuration he says is impossible. All right. I mean, there's nothing else to say here. And then the little crowd of morons pretends this was somehow relevant. He's 98 slates short of a roof. Called shingles, moron. I mean, he's really, he's still living. I mean, only the mega rich have slate roofs. Anyway, you can tell her 1,000 times, but she simply doesn't understand how physics works. So this is an explanation for why the Chevrolet video is a lie. Somewhere in here they explained. And does not want to either. That's okay. I just don't call everyone else stupid. Just don't call everyone else stupid. You just called people stupid and an idiot. I don't get you. That's overt duplicity. Amazing. There's no other way to argue this argument, is there? I mean, either I'm stupid or you're stupid, right? One of us has to be pretty fucking stupid because it's a pretty fucking obvious statement you're making. You're saying kinetic energy 1/2 mv squared is right, and you're saying you have good reason and it makes perfect sense and I totally understand it. Well, I'm saying I totally understand the MV thing. It makes perfect sense to me. I see all the evidence in support of it. I don't see any hope of your silly theory being the truth. So what do you think's supposed to happen? I'm supposed to just concede? No, you're supposed to show me it taking 4 times the fuel to go twice as fast. That's what's supposed to happen. You're supposed to show me the 5-ton train going 10 miles an hour pushing, okay, smacking into 2 10-ton trains and making them go 5 miles an hour. That's what you're supposed to show me. Show me that elastic collision. Show me the elastic collision where you conserve the kinetic energy. I mean, because if you do, you're doing something pretty miraculous. All right. Again, they won't do any. For 2 years, I'm drawing spaceships, I'm drawing levers, I'm drawing gears. They won't touch these arguments. They won't do the same thing. Draw it and explain how it functions and it works. Won't do it. All right, so that's enough of that. Jesus, just what a waste of time. So I guess I can get to Julia Sumner's video here from here. So this is lesson 3, and I played it before, but we'll play it again because with each rendition I become more astute at identifying. Oops, that's where they go wrong. You know, that statement they made isn't true. But in case there's a commercial, I'll take a pause. Alright, so here we are at the video. So I'm going to read this description just because it's kind of funny. I mean, there's a... yeah. Oh, look at all this extra stuff. Good. Let's see what we can see in here. Alright, it is rather obvious that it requires it is rather obvious that the greater the mass, the greater the inertia of a body. So he's already stated in a previous video that inertia is a synonym for mass. The harder it is to put into motion. Right, you have to give something enough energy to move it. Things won't move unless you give them enough energy to move. Okay, heavy things need more energy. If you don't have the energy sufficient to make it move, then it doesn't move. And in the case where you have to overcome friction, it's a real issue. Alright, that is, if a body of mass m requires a force F to give it so much motion. So again, you can understand this by just banging things with a spring into a brick wall. Okay, and then lighten the wall. So you can expect to get whatever the efficiency of a spring is, you can expect to get back what you put in from the spring if this is immovable. And all I have to do is start making it movable, and then all of a sudden I'm getting less and less from the spring. And the more movable I make this object, the lighter I make it, the more, okay, I don't get any reflection. I don't get anything back, and everything just goes that way. And the perfect scenario is I make this and this the same weight. If I make them the same mass, then I can just put all of the energy into this and conserve it perfectly. And when I start to go the other way, that is, I start to get lighter over here, I run into a similar problem where the light thing will go, but this thing continues on its way, so it still has its energy. It didn't get the energy in. But that's all that can happen, right? You can have the scenario where this is heavy, this bounces. When they're equal, the energy flows straight through, and when they're unequal, a portion of the energy goes into the lighter object, and then this one retains a portion. That's it. Momentum makes sense. Alright, and let's understand Newton said explicitly, you want to go twice as fast? You want something to move twice as fast? hit it with twice the force. That is, if a body of mass m requires a force F to give it so much motion, whatever that means, that is so much acceleration, then the body of mass 2m requires a force 2F. So right here he's basically saying there is no kinetic energy. So, just undoing any notion of F equals ma with their acceleration crap, because obviously they're saying it takes 4 times the fuel, 4F, to go twice as fast, to give it the same motion. These truths are tied up in Newton's second law in the mathematical form F equals ma, right, which Newton didn't write. Okay, when now a body held in the hand, say, is dropped to fall freely, the force urging it downward is its weight. The force, okay, is what you're collecting. You're collecting it. You're gaining velocity. It's tied up directly in your velocity. The force doesn't go through you. It doesn't do any of that stuff. It collects in the object and makes it go faster and faster and faster. The motion it acquires, its acceleration downward, is now g. That makes absolutely no sense, right? Because that's only in 1 second. You go g, small g, 1 second, g. Next second, you get another g. Third second, you get another g. G's are units. It's an amount. That's what g is. It's an amount you get per second, per 1 second. So that's another piece of mushy language. We call this acceleration of gravity for short. Accordingly, we write W equals mg, which, again, the work in 1 second. Again, you have to keep recognizing that the g is in units of per second units, in per second clumps. There is no g without the seconds tied to it. Thus, it is that F equals ma and W equals mg are analogous expressions. Now, obviously, they say work equals mgh, and then they say work in their work equation is force times distance. So why they're saying mass times the gravitational constant now, who knows? Because that's obviously not consistent with 1/2 mv squared. Alright, we show 2 cars, little one and big one, masses m, mass 2m, say. They are connected by a string. So we'll show the video, we won't bother doing this. But, clearly he doesn't really demonstrate that, to tell you the truth. He doesn't let the cars actually do their thing, as I remember. Alright, make sure this volume is not too much. It's probably a little louder than necessary. Moving on.
How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our special business today is Newton's second law. The second law. Now, in an earlier program, we discussed the first law, and I showed you some dramatic demonstrations on the first part, a body at rest, and on the second part, a body moving uniformly wants to do that. Now we come to Newton's second law. This is a staggering thing in its implications, and very, very difficult, really. But what students of physics learn somewhere in their course is that Newton's second law says F equals ma. And indeed, that's what it says. But that's powerful.
That's not what it says. So he says, indeed, that's what it says. That's not what Newton wrote. It's not Newton's formulation. Newton's formulation was F equals the change in your momentum over the change in the time. So obviously, basically saying it's going to be a rate. If you want the force as a rate, you just calculate how many units of time and to divide that into your momentum, which turns into just your velocity, and it'll tell you how much force was applied. So clearly you could just do force final. How much total force is just going to be the change in your momentum. The change in your momentum, the change in your velocity will tell you what the final force is. So if your velocity doubles, it was 2 units of force. If your triples, it's 3 units of force. It's just not that complicated. That's what Newton said. I'm just saying, Newton didn't say 1/2 mv squared. He opposed it.
And not so easy. Let us see what Newton said for his second law. In the Latin, mutationem motus proportionalem esse vi motrici. But the Latin is a little old-fashioned, so if we look at the English, here it is. Change of motion is proportional to force applied.
Meaning, pretty much, it's the same thing. By proportional, he didn't mean like 2 to 1 or 4 to 1 or 10 to 1. He meant it's 1 to 1. You want to go twice as fast? 2 force. You want to go 3 times as fast? 3 force. That's simple. That's what he meant by proportional. It's pretty much, he could have said, is equal to.
And takes place in the direction of the straight line in which the force acts. So,
obviously, in the sense that the forces can be reversed pretty simply, again, throw the tennis ball against the brick wall, and let's say it's rubber ball. And what do? You change exactly the direction of the force that you've thrown into the wall.
Let me demonstrate Newton's second law. Here I have 2 cups.
So it's a semi-demonstration, right? Because he's not going to actually measure anything. And so he's just going to say when there's a 2 mass and when there's a 1 mass. The 1 mass moves slower because they're being applied the same force, is what he's saying. But technically, and by kinetic energy theory, they're saying, no, it really isn't the same force. You've put much more energy into the smaller card. They're going to say the smaller card has more energy. So obviously it got more force from the rubber band. So there's no point in saying the same force is acting on the 2 objects. Same force isn't acting on them by the kinetic energy theory. Now obviously I believe the same force is acting on them, and I believe their momentum is the right answer, defining their energy, and there is no such thing as this twice as much energy in the lighter card. The 2 cards have the same energy, period. And if you let them hit each other, you'll see they'll have the same energy because one of them won't push the other one. The collision won't mean that one cart shoots in one direction. It won't plow, indicating, it won't like a car accident. It won't show you that if the heavier vehicle going faster hits the lighter vehicle going slower, it moves the whole collision in the direction of the heavier vehicle. That's what you're not going to see. It could be a lighter vehicle. So if a lighter vehicle going faster hits a heavier vehicle going slower that has less momentum, the faster vehicle, the lighter vehicle, will move the collision in its direction.
A heavy one, a massive one, and a less massive one, and they are connected with a pseudo-spring, an array of rubber bands, which are called elastic bands, but which incidentally are inelastic. Now they are on wheels so that they move rather freely, but we learned earlier that this one has less inertia than this one. Now when I pull them apart and stretch the spring between them...
So less inertia just means, yes, less mass by his own definition. You just showed us big M, little m. Obviously one has less mass. So again, the inertia thing doesn't mean anything. Just means that it takes more to fill the buckets. Bigger the mass, the more energy it takes to make it move. Because the energy has to move all of the masses, all of the atoms, all of the electrons, all of the protons.
The same force acts on both. And let us see if we cannot...
So it doesn't make much sense for him to say it when he's going to defend 1/2 mv squared, right? Well, he's not going to do it in this video. Oh, that's the catch. So even though this formula is how they derive their 1/2 mv squared formula, okay, he's not going to talk about kinetic energy. He's going to talk about momentum, ironically. And it won't be till the 4th or 5th video. Yeah, the 5th video, I think. Let's see if it's on the list. Yes, the fifth video, energy and momentum. Then he'll start talking about kinetic energy.
At once predict what will happen. If we apply Newton's second law to the forces acting on these cars, clearly the big car will have a little acceleration and the little car will have a big acceleration. That's an obvious thing to speculate on. Watch it.
Right, and the acceleration isn't what's going to hit each other. The velocity is what's going to hit each other. They're acquired acceleration. The acceleration's happening in increments. Okay, and they're acquiring velocity as they accelerate. It's the velocity that's increasing, not the rate of acceleration, so to speak. So it's really just about the velocities in the end. Big M, big little v, little m, big V. So yes, the lighter car will go twice as fast. Is what he's saying, confirming, basically saying, yes, momentum is conserved.
I'm going to pull them up.
Conserved in the sense that we don't know the total elastic pressure that this rubber band is placing on these two carts. And that's the catch, because what they'll do is do this experiment with two twice as heavy carts and then say kinetic energy says there's even more energy. So they've actually physically done that experiment. They take the same elastic band, stretch it to the same distance, put heavier objects on it, and say it made more energy. The elastic band only made 1,000 joules in this experiment. If I use two double the weight carts, I'll get 2,000. And go heavier, I get 4,000, presumably. Somehow making the objects heavier will get me more energy out of the same elastic stretch. Doesn't make any sense. I don't think it's true, and they certainly won't prove it.
Apart. There is one and the same force acting on both cars, and you will observe that the smaller one gets going the faster sooner. Of course. And so, here is an expression mathematically that describes...
So again, if he allowed the carts to crash, the obvious conclusion is they contain the same momentum. They won't go this way, it won't go that way. The crash won't show that this lighter car has twice the joules. So if I convert the joules into watts, we're basically saying I'm going to smash 1,000 watts into 2,000 watts. Somehow the 2,000 watts isn't going to push the collision in its direction. And you could turn it into, just I thinking of it in terms of heat. Something twice as hot as something else, and somehow the twice as hot thing isn't going to overwhelm the half as much heat. I mean, come on. No matter how you think of it, it just can't be possible this has twice as much of anything, because it really won't push the other one the other way.
This. And what do we learn from that remark? We learn that the accelerations are inversely proportional to the masses. The bigger the mass, the less the acceleration.
And again, he keeps talking in terms of accelerations when you're really not seeing the accelerations, you're seeing the accrued velocity. So the accelerations are the invisible part, the output, the thing that's going to matter is the velocity. The acceleration isn't going to matter because it's going to be accumulative. What really matters is what's the net velocity.
Now, this experiment with the two cars, very important for our concern later, because we will talk in subsequent programs about the energy possessed by each car.
Right. So now he's going to say there's this kinetic energy theory. Even though I can't show you that it has more energy, I won't in any way demonstrate that it has more energy. I'll just say that it does. I'm just letting you know that's, and again, this is just showing how he can't show it, so he has to just say it, and he's just basically saying, trust me.
And about the momentum possessed by each car, and we shall learn then that Newton's second law has enormous implications.
So again, he says it's Newton's fault when, again, Newton opposed what they're claiming. Okay, directly and through his surrogates made extensive arguments saying bullshit, calling bullshit. And the fact is he won the argument. Okay, while he was alive, people recognized the arguments and said, oh, okay, yeah, it doesn't make any sense. Let's not believe in mv squared. And it was 20 years, 30 years, 40 years after, 60 years after Newton's death, something like that. 1720, no, Newton died 1720. I just hate having to remember all this crap. Maybe it's 20 years after Newton's death. They resurrected this crap.
To work in physics. Now more about the second law. Here is a scale on which I hang a weight. And I don't care what the scale reads, it reads something. We say it reads the weight of the body. But I really don't know what that means. Nor did Newton, because as we believe, gravitational forces, the earth pulls on this, stretches the scale. But remember, even Newton said, I offer no hypothesis concerning gravitation.
Right, even though the hypothesis that, well, it's just photons does work. Yeah, it's just little corpuscles of energy. Yeah, that theory does work, does create an inverse square law, does fit the evidence. Anyway, so he's holding the scale, so we have to remember that's the immovable part.
Now, do we understand it today? But anyway, this scale reads the weight of this. So I'm going to write Newton's second law saying that very fact. Here it is. F equals mg, where mg is the weight of the body. Now,
so mg would be the weight of the body, would be basically its velocity again. So that works, but you have to recognize that the 9.8 meters is per 1 second, every 1 second. And all you're saying is that the net part that the scale can see is only 9.8 meters. That's all it can see. The first 9.8 meters is the only 9.8 meters you see, because the other 9.8 meters all go into the hand holding the scale. You have to push into the earth before the earth can push you back. It can't push you back first. So first you have to push in. That's what you see on the spring. That's the initial 9.8. And all the rest of them you're not going to see because the earth pushes them all back.
I'm going to accelerate this system upward. And I want you to see what the scale does. Watch it now. The scale read more. And so I have to add here.
So obviously you're doing more gravitational pressure if you move the scale with a velocity in the opposite direction that the gravitational force is functioning. Then the net force is bigger.
MA. In other words, the scale reads not only the rest mass of the body, but an additional force which was required to accelerate it upward.
Now, nobody would think in these terms, right? That this is a bizarre way of starting to write of a longer and longer equation that wouldn't be relevant when you just want to know how much something weighs in gravity.
Let me now start again in the zero position, the system at rest, the scale reading, the so-called weight of the body, and let me accelerate downward. Watch it. The scale reads less, and so I write minus MA, mg minus MA. And this tells us a wonderful thing, because
it tells you that, frankly, you can undo, okay, whatever effect the gravity's producing, okay, by essentially creating a velocity that's, by giving both objects a velocity, allowing the object to free fall. That's it. Yeah. So you're no longer applying friction. So all the dropping does is take away the friction. You've stopped allowing there to be any pull on the spring because you're not pulling on the spring anymore. You're not stopping the spring from moving. You're allowing the spring to fall.
if I were to go to the edge of my roof and hold this like this, and then let go of it here, and the whole thing fell down toward the earth, a good question to ask is, what would the scale read during the falling? And the answer is obvious. Since the acceleration downward would be that of a freely falling body, the scale would read 0. So if I should jump off from my tabletop, while I am in flight toward the earth, I am weightless. I am weightless.
And the weightless means you're collecting weight. So let's just understand, the whole time you're free falling, you're collecting the velocity. So when you hit the ground, you're going to weigh a lot. And that's the point. You're collecting the force. I mean, that would be the argument I would make, is the force is something you collect. Aye.
Now, this second law bears on the first one, which I showed in an earlier program. You remember that I had an enormous weight here, on which I pulled...
I don't know why he got redundant in so early an episode. Just because, come on. Yeah, you showed it in an early episode, so why do it the same thing again?
With the string, and the string held it. But when I gave the system a sudden acceleration upward, the string cannot endure it. And I said then that the body wishes to remain at rest. I now add an additional fact, that the string must exert a force not only equal to the weight of the body, but an additional one to accelerate it, which it may not be able to do. No, it couldn't do it. Now, what is the meaning of this for other things?
Thank you.
Supposing I had an enormous sphere, such as I have here, a steel sphere, 2 inches in diameter, and then a teeny-weensy one. And I want to show you that. In fact, here I have several of different sizes.
Yeah, this video really isn't too good.
There's one. Very good. Now, I have one in here that is so tiny, in fact, that I can't see it without my glasses. That shows you how tiny it is. And I wonder, if I get the other debris out of the way, can the camera get that little one? Right. Well, it's there. I assert it is there, even though you cannot see it. Oh, yeah, it's awful tiny. And what am I going to say about it? Supposing I hold these two, I won't hold the tiny one because you can't see it. Supposing I hold these two at the same horizontal level, above the level of the earth equally, and I let them go.
Right. So they're going to fall at the same rate because the little tiny one is a tiny bucket, can only collect a little tiny bit of gravitational force, right? And the one that's big has a big bucket, lots of little atoms to hit the force, lots of atoms getting the force sticking to, therefore it collects more force. Okay, so, and when they hit the ground, the heavy one's going to make a big dent because it collected a lot of force, and the little one's going to make a little dent because it only collected a little force.
So, they fall with the same acceleration. Proof. Newton's second law. Proof. F equals ma.
I really don't think that's a proof of the second law, so that's kind of funny. Because obviously it's in this bizarre context where if I drop it from 4 times the height, which looks like it's going to be 4 times something, it's really only twice the time. And that's the key point. It's only going to collect 2 units of gravity because the units of gravity come in timed units per 1 second. You want 2 seconds of force, you have to wait 2 seconds in free fall.
Is the generic expression for Newton's second law. Now, what is the F acting on this body? The F acting on that body is its weight. And when I let it go, what is its acceleration? It has a certain...
So the weight is, he's saying F equals momentum, right? What else could weight possibly be but momentum? I can duplicate the weight you weigh on a scale by just opposing a momentum on the scale. So I can make something weigh what you weigh in gravity. I can just push something into here, say this is 100 pounds. You weigh 100 pounds this way in gravity. I can just move the scale this way, and then I can just create a momentum that'll duplicate your weight. And I can do that with your weight. I can move you a certain speed into that scale, and at that speed you will duplicate perfectly what gravity's doing, except you'll be moving horizontally. And the only difference would be I have to create a constant force if I want to have a constant weight on the scale. But the fact is I can create a momentum that'll create that as an impulse.
Mass m, its acceleration is g. So these two equations, you see, this the generic one, F equals ma all over the universe, so we think, and W equals mg for earth-dwelling creatures who wish to look at the weight of a body. So you can...
So they just said it again, basically just repeating the same thing. Weight is momentum, and momentum is your velocity being created by gravity. So again, but understand, gravity is in the form of a per second rate of acquisition of force. It's not a number. It's really not a number. A rate isn't a number. You have to actually calculate how many seconds you're in the gravity before you have the actual number of the g. The g has to be calculated. If you're only in the gravity for a half a second, then the number is not going to be 9.8. It's going to be 4.9. And if you're in a quarter of a second, then it's going to be, whatever, 2.49 or whatever.
See that if I doubled the mass of any body, I would at once double its weight, and its acceleration remains unaltered, which is a sort of explanation.
So it just basically, again, is just pure momentum there. It's just all momentum. He doesn't put in the kinetic energy nonsense.
Why all bodies have the same free fall acceleration, as Galileo showed in the 17th century.
And the reason they have the same acceleration is because the force is proportional to the mass. Period. Period. You collect more force if you have a greater mass. You collect less force if you have a less mass. Period.
Now, this is quite remarkable, because one is led to think, why? I can't believe that this one will not fall faster than this one, and this subject is taken up very excellently by Galileo in his dialogues concerning two new sciences, where I urge you to read the discussion between Sagredo and Salviati and Simplicio. Now...
Yeah, Simplicio was the Pope, apparently. So that was funny. Got him in a lot of trouble.
There are some further implications of the second law, which have some levity. I like physics in cartoons, and here is a cartoon that I recently saw. Here is a little boy, and...
I thought it'd be the Roadrunner. That would be a better cartoon. Roadrunner runs out to the... Oh yeah, and he just stays out there. Yeah, no, I can't do that.
And there is a bathroom scale, and here is another little boy, and they weigh, by all looks of things, about 70 pounds. Now, it's obvious what has happened. This one jumps down onto the scale. And what is the caption under the picture? Wow, he says, wow, 140. You can see that this is Newton's second law. F equals mg plus ma.
Right, now you can only weigh 140 if you jump 1 centimeter. So you can only double your gravitational weight by falling 1 centimeter. That's what it takes. 1 centimeter, double. Something like that. 8 to 10 millimeters of height will produce twice the weight. So if he weighs twice as much, the only way this could be true is he only jumped 1 centimeter. He only fell 1 centimeter. So again, the cartoon, he says he saw a cartoon. Well, the cartoon isn't accurate.
Because of the force delivered through his acceleration to the scale. And I think that's terrific.
Except it's totally misleading. And it's totally misleading, right? So if you drop from something like a meter, okay, you're going to weigh a lot more. Like, the 70 to 140 is going to be more like 1,000 pounds.
Let's consider another such problem. Here is a smooth pulley fixed, say, to a solid beam up there. And here is a rope over the pulley. And here one man stands holding the rope. And here an identical weighted man stands holding this rope.
This is all interesting, pulleys, and so it's all about how you attach them. So if you attach the pulley to the ceiling, you're not going to gain any mechanical advantage. But if you actually attach it to the individual and then have two ropes going over, then he'll weigh twice half as much.
And they are both on the ground. Question. The man A climbs the rope. B just holds on. He just stays there. Question. What happens to B? Answer. B gets a free ride. For whatever A does is felt by the rope and in turn by the man. And so, this is really Newton's second law. Two men on a pulley. Now...
So that's also kind of dubious, right? Boom. Because all you're saying is there's a tiny bit of friction in the pulley. And if the two men weigh the same, there's not going to be a decisive winner in the force being applied.
A more dramatic event. Much more dramatic. Here is a scale which...
So this was good because it does seem confusing until you realize, there's two ropes involved.
reads from 0 to 2,000 grams, and I put 1,000 on it, and clearly the scale reads 1,000. If I put 2,000 on it, at rest, remember, at rest, the scale reads 2,000. Now what am I going to do? I am going to put the scale on a horizontal plane on that board in such a fashion with a pulley here and a rope and a pulley here and a rope, and I'm going to put 1,000 there and 1,000 right there so that I have 1,000 pulling to the right and 1,000 pulling to the left. I'm going to do that right now. There's 1,000 on the right.
So he doesn't give the answer, which is annoying.
And I've got to hold that. Now I get over here and I put 1,000 on the left, and then I cover it over, as I like to say for my students, so that evil eyes do not see it. And remember now, we ask the classic question.
2,000, yes.
When I had 1,000 on the scale in the vertical line, it read 1,000. When I put 2,000 on it in the vertical line, it read 2,000. We want to know, what does the scale now read? 1,000 pulling to the right, 1,000 pulling to the left. Several answers. One, oh, says somebody, it reads 0, since the forces annul each other. No.
No, that would be retarded, but okay. Yeah. Obviously, the spring doesn't see it as an annulment.
Oh, says somebody else. 1,000 to the right, 1,000 to the left, it reads 2,000. And I must tell you that whatsoever your point of view, these are both wrong. So, I could leave it as an exercise for you to...
Oh, okay, so it has to read 1,000. Because, yes, the 1,000 pounds is exactly the same as when you're holding it, because you're holding up the continuing gravitational weight. So the gravity's a constant force, you're holding up the constant force, you're holding up against it. You have in your hand the weight of the spring and the weight of the scale when you're holding it. So obviously you're applying 1,000 pounds when you're just holding it steady. It's already 1,000 pounds of pressure this way that you're already applying. So when it reads 1,000, it's because you're applying 1,000 pounds the other way to undo the constant force. Again, it's the constant force part. If you were just doing an impulse, this wouldn't be the same issue.
But since I have a kind heart, I will tell you that the scale reads 1,000 grams.
You did tell me.
But having told you this, I urge you very seriously to explore why that is so.
Yeah, right. So he doesn't give the explanation. The explanation is when you're holding the weight, you're already doing one of those thousands. And so the other 1,000 is just doing the same thing as it did when you hang it. It's just applying 1,000 pounds to the other side of the spring. So you're applying 1,000 pounds of counter force by holding it. But that's only because gravity is a constant force. And you have to initiate the application of the force. So somewhere the spring's compression, the expansion of the spring happened, and you didn't have to deal with that force. That force got consumed by the spring's expansion, and you'd encounter it. But all the other milliseconds of gravitational force, you do have to hold against.
Further little comment. Oh, I want you to see another picture of Newton. I showed an earlier photograph in his later years, and here is one.
I don't think it could be a photograph, frankly, right? Died in 1720. I don't think they invented cameras till like 18-something.
As a young man, 17 years old.
So, yeah, it doesn't look like a photo, frankly. But anyway, right? I don't know if they have any Civil War photos. I don't know. Not Civil War. Yeah, Civil War.
When he entered Trinity College in Cambridge, a genius the like of which the human race has not yet again seen.
Right, so I know in the 1600s they didn't have no camera.
One last experiment. Newton's second law. Here I am going into an elevator on the ground floor. The push of the floor of the elevator when at rest is my weight plus the weight of the bag. Now the elevator accelerates upward. You know what happens. Your knees buckle and the load is pulled out of your hand. No, not pulled. It wanted to stay at rest. It was at rest.
Yes, it was pushed. But anyway.
And that's what it tried to do. But what is the explanation of the added tension in my arm and the bending of my knees? Answer, F equals mg plus ma. Now the
Well, that's kind of a bogus answer.
elevator's on an uppermost floor and starts down. You know what happens? Your belly feels empty. F equals mg minus.
The force is being applied indirectly to you. So you're not getting it directly atom per atom. You're getting it from one part of your body, and it has to go through your entire body to get to anything. So the suitcase doesn't know what's happening except for your hand's motion. Your hand has to give it the change in its velocity, because that's the contact point. It's not on the floor. It's in your hand. So obviously all the force telling the bag it has to go somewhere has to go through your hand. That's why you feel it. I think that's a better explanation. That gravity isn't the same as an elevator moving. There's no perfect equivalence. In one case, every one of your atoms is being hit by the force individually, and in the other case, only a part of your body is encountering the force, and therefore it must be transferred through the rest of your body, and that takes time, and that you're going to notice. And it's never going to be equal. It's always going to be unequal, and you're going to elastically react to the unequalness.
Minus ma. And so we have a better understanding of the laws that envelop us by applying the laws of Newton.
So let's understand. They've converted the second law into the excuse for the 1/2 mv squared. And frankly, everything he talked about could be explained as momentum. There was no examples of anything that involved anything taking 4 times the force to go twice as fast. All right. Even though Newton didn't say that clearly. Newton said the same force. All you need is a force. The force will make the momentum in equal proportions. 2 units of force, 2 units of momentum. All right. Yeah, that's enough.
And I thank you for your attention.
It's a lament, I tell you. It's a dirge, arguing reality with morons. All right, so I think that's enough of video. Okay, we continue to wait to see if somebody can do a simple kinetic energy experiment demonstrating its existence, proving that friction is the same no matter how fast I go across this scale. I will compress it the same amount because I can't change how much force I'm applying to the scale by quickly going through the gravity, because gravity's not like a paint sprayer. something like that, or showing how spaceships navigate based on how much joules of energy you're producing. So if you shoot 5,000 joules out one side and 1,000 joules out the other side, oh, that's right, you don't move. Because 5,000 doesn't take 5 times the work to produce. No, I just, shoot a gun. Yeah, and it does it for me automatically. The gun automatically creates all of the extra energy for free. And I don't have to do any work. Extra work. Just shoot light things, and you're making free energy. That's their theory. All right. So, yeah, that's enough. Yeah, I think so. I'll pause and see if I have anything else. There's no point. So, I'd like to make a live video if somebody can actually draw a lever or do something interactive, where they actually play my clip, my video, portions at least, and explain where I'm making some catastrophic error in my illustration of the function. But till then, there's no real argument taking place because there's no counter argument to any of my arguments.